So next up, presenting quantitative data. So again, the first thing we're going to look at is a frequency distribution table. All right. So sometimes it's going to look exactly the same as we saw before. So for example, let's make a frequency distribution for how many math classes people had taken. So the data that we had was 11, 11, and 2. So how can we make let's make the table for that. What do we do? What are the data values? Right. So we don't really need a 3 because anything that has 0 in it you can once you hit everything that you have, you don't need to keep writing 3, 4, 5, 6, 7, blah blah blah. But it is important to write the values in the middle, even if there's 0 in there, just for spacing reasons. Okay. So and the frequencies are, of course, 11, 11, and 2. And what about the relative frequencies? (11 out of 24, 11 out of 24, and 2 out of 24. So you can see writing that relative frequency as a fraction is actually pretty easy. Okay. Okay. So notice in this case, it pretty much looks the same. It's very easy to make the frequency distribution from our data. So when might it look different? Well, suppose I do this survey. I say, what is your age? And I take a sample from all BMCC students. And I get these responses. So how are we going to make a frequency distribution table with this data? Yeah. Does that make sense? Okay. In particular here, it makes clear intuitive sense why you'd want to do grouping, and you wouldn't want to say 19, I had one person, 20, I had one person, blah, blah, blah. Okay. So as Shabin said, you're going to break it up into groups. Groups of data are called data classes. Now, what class you choose is up to you, but let's see. 2 things. First of all, typically we're dealing with ages. What's a nice typical way to break up ages? Yeah. 10s, 20s, 30s, blah, blah, blah. So that's what we're going to do here. Each group is called a class. Okay. So how would we make the table for this data? So what's the first class? Okay. Now informally you can say 10s, but let's do this using math and statistics. The way we would write this down is we would say this class goes from 10 until what? Can't say, yeah. You want it to be from 10 to 19, because what's your next class? 20 to 29. Now, what if you had said the first class is 10 to 20, and the next class is 20 to 30? What's the problem? Where does 20 go? Make sense? Okay. So 10 to 19, 20 to 20. Wait. Let me get this on the lines. Okay. So 10 to 19, 20 to 29, 30 to 39, 40 to 49, 50 to 59, and that covers everything. Okay, so what's the frequency of the first class? 1. What's the frequency of the second class? 7. Frequency of the third class is 1. frequency of the fourth class is 2. Frequency of the last class is 1. Now let's get relative frequencies. What's the relative frequency of the first class? What do we have to do? What do we need to do? Yeah. Which gives you 12. So the total is 12. So the relative frequency for the first class is 1 out of 12. And the relative frequency for the next class is 7 out of 12. Well, you know what? It's etc. So let me just write all these in. Okay. And because I'm going to want these later, I'm going to put in the decimal for the relative frequency. So we made a decision. We said that we want our data classes to be 10 to 19, 20 to 29, blah, blah. That decision is called the class width. So the class width is the distance between the classes. So what's the distance between two classes here? To get from one class to another class, how far do you have to go? Say it. It's 10. The first class starts at 10, the class starts at 20, then 30, blah, blah, blah. So you're hopping by 10s. That's your class width. Okay. So generally, we like to keep the class width the same. Now, when you're doing a demographic survey, it might make sense to break it up into groups like 18 to 24, 25 to 34, 35 to 49, 50 to 65 or whatever, because you want to break this up demographically. However, for doing statistical analysis, typically we like to keep the class width the same to help out our calculations. Okay. The class limits, also called the class boundaries, are the highest and lowest values in the class. So, for example, what's the lower class limit for the first class? 10. What is the upper class limit? The upper class limit. Upper meaning bigger. 19. That's it. This is your first class, the 10s. What's the lower class limit? In other words, what is the smallest value? 10. Upper class limit. Biggest value. 19. That's it. So one little wrinkle is, how would you do this? How would you make a frequency distribution table with continuous data? Right, in this case, we have integers, so it's easy to say, goes from 10 to 19, my next value is 20, that's in the next class. How do you do that with continuous data? You just adjust the class limits according to your precision. For example, think back to what's an example of continuous data? It's the temperature outside. Well, whatever the temperature is outside, however you measure it, you're going to stop at a certain number of decimal places. Or we can actually do this with age. Suppose you record people's ages with 2 decimal places. You can figure out, you say, how old are you? You're 20.47 years old. Okay. Then what do your class limits have to be? Your first data class would go from 10 up till what? 19.99 exactly. Any questions about so far? Ready for the next thing? Okay. Next bit, histogram. What is a histogram? What kind of chart? Sorry? Columns, sometimes bars, but yeah. Okay. So basically a histogram is a bar graph for quantitative data. So again, it's going to look about the same, but with some small adjustments, which I'll mention. Okay. So let's actually make a bar graph for the number of math classes. So how do we do that? How many people had taken their math classes? 11. How many people took one math class? 11. So you draw a bar that goes up to 11, where your category, your data values go on the horizontal axis, and the frequency is measured on the vertical axis. You can flip it around, but it's usually done this way. Okay, and then what else do I have to fill in? Yeah, so 2 was 2. So now, what do you do if each class contains several values? So for example, how would you draw a histogram for our data regarding ages? So certainly you're going to want a bar that's 1 high, then a bar that's 7 high, then a bar that's 1 high, etc., etc. But how do you label this and how do you set this up? Yeah.
The class group on the bottom, and I think the frequency on the left.
Okay. So pretty much yes. With one minor adjustment. We could write 10 to 19, 20 to 29, 30 to 39, but it would be messy. So a slightly more elegant way to do that is just to mark off 10, 20, 30, 40, 50. So then, for example, when we draw our bar that's 1 high, it's understood that this represents 10 and up to, but not including 20. You could think of it as an open interval, absolutely. Open endpoint. Okay. And then for this one, we had 7 people. So that's 7 people from age 20 up to, but not including 30. And then we can fill in the rest. So 1, 2, 1. Like that. So 2 notes, 2 comments about these things. Let me see. Okay, so first of all, how is this picture different from the picture of a bar graph? It's a subtle difference. Yes, they're together. And the question is why? There's actually a reason. So again, so compare this graph with this graph. Basically, yeah. Absolutely. Okay. So let's think about let's think about what this means. You are You're 17, you're 18, you're 19, and then what happens? And then you're 20, and then you're in the next group. These values, they're numbers, so there's actually an order to them. As soon as you leave one group, you're in the next group. Does it make sense to say the same thing about what your major is? Can you say that as soon as you're a little bit past computers, you're in accounting? No. That doesn't make any sense. So these groups are separate. So that's why on the graph, on the picture, the columns are separated. But whereas for quantitative data, they're next to each other because it's all connected. Okay. That was the first point. The second point is we've made this histogram for frequencies. We can do the same thing not for frequencies, but for relative frequencies. So how do we do this for relative frequencies? Let's see. So the total for frequencies, the total is 12. For relative frequencies, what's the total? The total is the total relative frequency is 1. So instead of scaling it out of 12, we scale it out of 1, and we mark this off. So if you recall, I did actually fill in the relative frequency values for these things. So I'm going to use that right now. So this goes up to here. This one goes up to here. This is the same. This goes up to here. And this goes up to here. So for example, 1 out of 12 was 0.083, 7 out of 12 was 0.583, etc., etc. Now what do you notice about these two pictures? About the graph on the left and the graph on the right? They're almost the same. They look the same. The only difference is that instead of writing 12, we're writing 1, or another 12 over 12. So instead of this bar being on the left, the bar is 1 high. The height is 1. On the right, how high is the bar? 1/12. Here, instead of being on the left, the bar is 7 high. On the right, the bar is 7/12 high. So that relatively, everything is going to be the same size. 2 is going to be twice the size of 1 on the left, and on the right, 2/12 is going to be twice as high as 1/12. That's why the pictures look the same. The difference is, are you scaling it out of 12 for frequency, or for relative frequency, scaling it out of 1? Yeah? Yeah. I mean, mathematically, that's exactly right. So the next sort of visual presentation is called stem and leaf. And I'm going to take this data set and I'm just going to start writing it down in stem and leaf format. And then as soon as you know what I'm doing, you tell me. Did y'all figure it out yet? Okay. So what am I doing? Right. So far I've gone up to 32. So my next data value is 22. How do I record that? Where do I put the 2? Next to which 2? So for 22, I write down a 2. Where do I write it? No? Oh, next to the 2, that's a stem. Okay, well, it's not next to it. It's in that row. Okay, but yes. So in the 2 row, I put 2. Next is a 47. So I need to make my 4 my stem and my 7's my leaf. 25, in the 2 row, I put a 5. 24. 42. If you want to be really super organized, you can go in order, but this is fine. Okay. Now, what's nice about this representation? I'll grant you it's simple, and you can what? I mean, you can always put your data in order if you want. Okay. You can easily read what? Yes. Okay. Now, what presentation that we've seen already today does this remind you of? Is it similar to? And I'll just draw in some lines while you think about how to answer the question. Does this remind you of anything? Yeah. Technically a histogram, but yeah. It's just a histogram turned on its side. Because the arrangement of the numbers basically makes up your bars. But this is better than a histogram because why? Yeah, all your data is excuse me. All your data is there. But isn't it in order? How does your histogram go? It goes your 10s, your 20s, your 30s, your 40s. No, I mean, isn't that how this is set up? Right. Well, you can put them in order if you want. But so like someone said, it preserves all your data. When would you not want to use a stem and leaf diagram? Yeah. That's true. You can't use it for qualitative data, of course, because there'd be no stem and no leaf. That wouldn't work. When else would you not want to use this? When what? When there's a lot of data. What if you have 10,000 numbers? Would you want to do this? First of all, you would want to do it by hand, but even if you had a computer to do it, would you really want to have 10,000 digits swimming around? No, you wouldn't want to look at these things. So this mostly makes sense for small data sets. Okay. Okay. So how would you make a stem and leaf diagram for this data? What's your stem? 10 and 11. And your leaves would be 5, 7, and then coincidentally 5, 7. You dig? Okay. Now, what do you do if your data has a big gap? And this is true for excuse me. This is true for stem and leaf, but this is also a good general note about graphing. So one way to handle this is in the naive way. Just say, well, I'm just going to keep marking off 40, then here's 50, here's 60, here's 70, here's 80, and I really have to keep going. But you might run out of room and you might not want to handle your data this way. So what's an alternative? All right. So do you know it? Okay. So this is a notation or a convention. So that squiggle on the axis means that there's a break in the values. Now, so in this way you can stop and then pick it up wherever you want. Now the good thing is that it lets you handle big gaps without worrying about using up too much paper. But what's bad about this? Well, it's kind of misleading. Because what usually comes after 40? 50, but here after 40 comes 100. All right. So you sort of have to keep it in your mind that this represents a big gap, however big the gap is. Yeah. Yes, I forgot to put 50 and 60. Gonna be all technical about it. Fine. Okay. All right. So next, we have what's called a frequency polygon. So what is a frequency polygon? It's a histogram, but instead of using bars, you use dots and connect them with lines. So what do I mean? Well, it looks like this. So can you see where the histogram used to be? So another way to think about this is, here's the old histogram. How would we convert this? How do we instead write this as a frequency polygon? Looks like this. I think by convention you put the dot in the middle. Yeah.
You can put it
I'm not going to be picky. Just put the dot in about the right place. Okay. So that's a frequency polygon. That's where that comes from. I think it's pretty straightforward. Okay. So any questions so far? Jermaine, it's good? All right. So the last one is a little bit sneaky because we have to introduce some new things. So it's Ogive. It looks like Ogive, but it's called an Ogive. All right. And Ogive presents the cumulative frequency. That's something new. We've talked about what that is. Okay. So the frequency for the first class is 1, then it's 7, then it's 1, 2, and 1. So the first class has 1 in it. After the second class has been counted, how many do we have so far? How many? 8. That's your cumulative frequency. After the third class has been counted, how many do you have so far? After the fourth class, how many? 11. And after the fifth class, 12. So that is your cumulative frequency. It's how many you have so far. And of course, we can always mix things up a bit by doing the every idea all together now. The cumulative relative frequency. So what is the cumulative relative frequency for the first class? Y'all? 1 out of 12. What is the cumulative relative frequency for the second class? 8 over 12. For the third class, yes. Okay. So, once you've hit the second class, how many do you have so far? How many total so far? That's it. Yep. Okay. So we now know what cumulative frequency is and how to find it. So now we can make the picture. So it's just the picture for an ogive is just a frequency polygon, but using cumulative frequencies. So it's just this. So of course, it starts at 0, and then after the first class, it's 1, so you have a dot at 1. Then after the second class, it's a total of 8, so you have a dot at 8. Then 9, then 11, then 12. And just connect them all with lines. And then same thing, but cumulative relative frequency.